let's start the funny derivative. Firstly, we have f of x. I am very short as e to the x squared over 2. Very, very fun equation. And let us denote the derivative of order n as f n of x, and we will see what that is. But first, let's just start taking derivatives. See what happens. So first, let's see f prime of x, and just gonna spare the details and just quickly chain rule this x e to the x over 2, and here you can see like that just equals x f of x. And this will be more important like later on. And let's take a look at f double prime of x. And let me just product rule this. First, let's just get the derivative x out of the way. So we just have f of x plus, x f prime of x. And f prime of x is just x f of x. So that'll just be f of x plus x squared f of x. And we're seeing now here that like you can write everything as a sum of f of x and like powers of x times f of x. But let's just take the third derivative. See, just to make sure, I can't be bothered to write the little apostrophes now, so just gonna get a 3 there. And again, f of x is just f prime of x, and then gonna product rule that. And first we have what, a 2x f of x and a x squared f prime of x, and that's going to equal, let's just rearrange. Well, firstly, the f prime of x's get subbed in as x f of x plus 2x f of x plus x cubed f of x, and these will add up to be 3x f of x plus x cubed f of x. And so I think it's pretty safe to say that fn of x, or well, let's use k. I feel like using k. Can be written as a sum from, actually no, we don't want the k, we want the n, because I want to use k here. K from 0 to n of some constant. Let's denote that as c sub k of n. That'll make a bit more sense later. Times x to the k, didn't like that k, f of x. And this is a bit hand wavy, but I think the proof by induction should be fairly simple. But like it's pretty simple to see, like every single time you're gonna end up with this last term that's going to product rule into an f prime and the original power, and that's going to carry over, and yeah. But let's take a little bit of a closer look at where exactly each of these terms is coming from. And so it's probably easier for the highest derivative, the third derivative. So we have this 3x f of x term, and if we go back a step, that came from the x f of x and the 2x f of x, which each came from the previous derivative. From the x f of x came from the f of x, and the 2x f of x came from the x squared f of x. And from there we can see that really any order, for the exponent, let's just call this any like exponent of x term is going to come from the one immediately preceding it and immediately succeeding it from the previous order derivative. So, and of course on the very ends, it's just going to come, on the very ends, it's just going to come from the one immediately next to it. And because this x term came from the x is 0, which is a constant term, and the x squared term. The x cubed term just came from the x squared term. And this can even go further back. So the constant term here came from the x term of the previous derivative. The x squared term also came from the x term of the previous derivative, because that was the only term. And it even goes back to the very beginning, because the x term came just from the constant term. And from here we can start to write out what c sub k of n is. We can say that c sub k of n is piecewise 0 for, actually we're gonna, a little bit of a mistake, we're gonna swap this to be c sub n of k. That'll make more sense. For k is less than 0, just to keep it generalized to all integers, and then c sub n minus 1 k minus 1 plus k plus 1 c sub n minus 1 of k plus 1. For the sake of clarity, we're just going to move this over. And this will be for 1 is less than or equal to k and is less than n. And 1, that's a terrible one. 1 for k equals n, and 0 everywhere else, which is k is greater than n. So quite obviously, because both this and this are outside of the bounds of the summation, those are just going to be 0. And here we have a recursive definition of the constant, and these terms correspond to where each of the terms is coming from. So the c sub n minus 1 of k minus 1, c sub n minus 1 refers to the previous derivative. And then the k minus 1 refers to the order of the exponential, like right below it. So for the x f of x term, that'll refer to f of x, which is going to, if say the constant over this f of x is just 1, and we see really, like, from the amount that f of x this f of x term contributes to the next x f of x term is just 1, that constant, because it contributes this x f of x term, which came from the f prime. And then the other term came from also the previous derivative, denoted by the c sub n minus 1, but it came from the order of the exponential above it, that being x squared. But because of the product rule, well, because of really a combination of the product rule and the chain rule, the x squared, to get to like the x term, by the power rule, it needed to bring the 2 out to multiply to become the x term. And here we see that happening here with the 2x times f of x. And so that's why we have also multiplied by this k plus 1 scalar. And so yeah, that's a recursive definition for each of these constants. And really from here we can get exactly what each of these constants is if we just want to like recurse back, but we can do better. We can do better. Here there's quite honestly a little bit of hand waviness, but we can consider this as traversing a graph. And for say, let's just take the fourth derivative. The fourth derivative will actually, no, third derivative, just because we've already done that and we can check this. So for the third derivative, it'd be like traversing a graph of dimension 4 of a matrix like this 3 times. And the reason for this is because the original function we're starting, it sets like a start point of this like x to 0 like constant term of c being 1. And this constant term, if I can just do a little bit of a diagram off to the side, this constant 0 term can go 1 to its immediate right, and we're just going to bring this arrow down into the constant term, in the constant 1 term. And this constant 1 term, because in the next derivative, it'll contribute to both sides of it. This will contribute to also the constant term and also the second order term. And that's again as a result of the product rule from over here. This 2 gets multiplied out and contributes to the one order higher than it. The first order term contributes to the one immediately to the left and to the right of it. And then the same thing happens again here. The constant term will contribute 1 immediately to the left. And we're gonna annotate how much it contributes as well. So far it's just been 1, right? But here, when this goes backwards, it'll contribute 2 because of the product rule again. The 2 will go out and multiply. And then it'll also contribute to the next term, just 1. And because of this, we can see that it's really like, you can define a sort of like ability to traverse here, because so here we can, if we annotate this graph a little bit, we can call this like 0, 1, 2, 3, 0, 1, 2, that's not a 2, 2, 3. So again, the constant term is able to contribute 1 to the first order term, that being this arrow, and the constant term contributing to the first order term. The first order term is able to contribute 1 to the constant term, as well as 1 to the second order term. Here we can see that again, the first order term is contributing 1 back to the constant term and 1 to the second order term. Then when we get to the second order term, we can see that that is able to contribute 2 over backwards, actually here, yeah, 2 over to the first order term, and 1 over to the third order term. 2 and 1. Now, there is no third order term, but we do have to make the matrix square, and this does keep it consistent. And with like how we expand the matrix into higher dimensions, where if we were to make this a bit more generalized, we would well, firstly, let's just see what this matrix is. Just bring, I've got a Matlab script for this. This will be zero, 3, 0, 1, 3, 0, 6, 0, 0, 12, 0, 5, 6, 0, 15, 0. And what we can see here is that this first row exactly corresponds to the coefficients C3 of K. And see from here, there is no constant term. And 3 is the coefficient of the first order term, 3x f of x. There is no second order term. And 1 corresponds to the coefficient of the third order term, x cubed f of x. So why is this? Well, after seeing that we can model this with like traversing a graph, the initial function f of x sets a starting point at the constant term. And so what we really care about is where and how much the initial constant term can traverse to, which is why we look at the first row, which defines the number of paths between the constant term and each of the other terms. And so there are 3 paths from the constant term to the x term, and 1 path from the constant term to the x cubed term. And of course, we're looking at paths of length 3 because that's how many times we're taking the derivative. And I say how many paths, but this isn't just the elements of the graph are not just 0 or 1, but I still say how many paths, because I view when something like this happens of x squared going to 2x f of x as contributing 2 different possible paths from just a single node. And yeah. But now let's see if this actually holds up. Let's see what happens with the matrix of dimension 4. I will actually write this out. 1, 2, 3, 4, 5. 1, 1, 1, 1. And as the way that this is generally defined, I'll write it out a bit later, but the entire major diagonal, all zeros, the diagonal right above it, all ones, and the diagonal right below it, going 1, 2, 3, 4. Because this just increments up, because this is basically traversing backwards. And when we traverse backwards, we see, again, from over here, we're using the product rule, which is why we multiply out the exponent, and these correspond to the exponents. Because 0, if we count the rows starting from 0, we have 0 for the constant term, 1 for the x term, 2 for the x squared term, and so these will correspond to the exponents. And then just gonna put 2 big zeros over there. The fourth power And we're just going to put that through Matlab again. That will be 30601. And honestly, we don't really care about what the rest of the matrix is. And so theoretically, the fourth derivative should be 3f of x plus 6x squared f of x plus x to the fourth f of x. So let's see if that's true. I don't need these anymore. Just gonna erase these. I'm gonna keep the third derivative because that'll be useful in getting the fourth derivative. F4 of x is, so here we have the 3, and we're going to product rule the xf of x into what? F of x plus x squared, or I'm doing that a bit too hastily, f prime of x plus 3x squared f of x plus whatchamacallit, x cubed f prime of x. And we're just going to distribute this 3 in and sub in the f primes for the x f of x's on one step. We get 3f of x plus what, 3x squared f of x plus 3x squared f of x plus x to the fourth f of x. And that will be our 3f of x plus 6x squared f of x plus x to the fourth f of x, which is exactly what we get from the matrix. 3f of x plus 6x squared f of x plus x to the fourth f of x. So we can say, back to this board, that for the nth order derivative of f of x equals e to the x squared over 2, that we can construct a n plus 1 by n plus 1 matrix. Let's call that M, where M is, we're going to go zeros along the diagonal, ones along the minor diagonal directly above, and 1, 2, all the way to n in the minor diagonal right below, and then zeros everywhere else. Hopefully that is clear. And construct matrix M, and the first row of M to the n will we will denote the elements just in order, C0 to C Cn. And f, the nth order derivative of f will be the summation from k equals 0 to n of ck xk f of x. And yeah, that's it. If you want to take a look at the Matlab script, you can find, I'll probably put that in the description. Maybe, I don't know how embedding files works, but if I can't embed it, it's a pretty short little function, so I'll just copy paste it in. But yeah,